but there's also some sort of low-level deep dives into the code as well, which if you're interested in the actual internals of how it works, those are quite useful. I hope to kind of get a feel for what's going on and hopefully understand the reasons why things work the way they do. All of the stuff that you're going to see tonight is also online. So that bit.ly link there, bit.ly/let's talk HTTP60 is a copy or version of this slide deck. It's not this current one, but it's pretty close. And there's a bunch of links in there as well to all of the resources and things. And feel free to check those out. And as I say, ping me if you have any subsequent questions.
One more on that, Steve, as well. The session is recorded. So if anyone wants to rewatch this later on, it'll be on our YouTube channel. So I'll put that in the chat.
Always good for revision later on. Cool. So the reason I wanted to sort of talk about this topic, and I've done it quite often at quite a lot of different locations, and it always seems quite popular because unfortunately, making HTTP calls in .NET correctly is not necessarily as straightforward as one would hope. The types are all quite clear to find, but there's certain nuances to how we use them and certain internal details that you kind of have to know. That's sort of a bit of a leaky abstraction in terms of understanding what's going on inside in order to use it correctly. And so I sort of come across this enough that I thought it would be a good idea to kind of deep dive into some of the classic pitfalls that people come across, some of the features that have been introduced as well through .NET Core sort of 2.1 to 3.1 that kind of help with some of the problems as well, so that you can get a feel for, whether you're using it correctly in your code bases and perhaps take a look at, updating them where necessary. So in terms of what I plan to cover, we'll probably spend about sort of 60 minutes and we'll talk about things like why do we need a feature called iHTTP Client Factory and what is it? How do you use it? We'll talk a little bit about the concept of outgoing middleware. So if you've used ASP.NET Core, you'll have already come across middleware, hopefully, for sort of incoming requests. They travel through the middleware pipeline, and it's a great place to apply cross-cutting concerns in ASP.NET Core applications. With HTTP Client, we have a similar concept that we can apply for outgoing connections as well, so that we can actually apply cross-cutting concerns on our HTTP calls on the way out. We'll talk a little bit about how we handle transient type errors, particularly using a library called Poly. We'll look at some other patterns and recommendations. These are sort of some of the things that I see, in code reviews and things that I tend to correct and that are just not that obvious unless you've shown them. So I try and sort of point them out and show them in code. We'll talk a little bit about the HTTP improvements generally that have been made through the code base. I am generally speaking about .NET Core in this session. So if you're using .NET Framework, some of what I cover will be applicable, but the implementation in .NET Framework is different. And there's a few different sort of ways of configuring it that aren't available in .NET Core. So most of this is guided towards .NET Core, but I'll call out if I can to any sort of .NET Framework sort of relationships. I've just added a slide in today actually to update one of them to cover some stuff in .NET 5, which is pretty new. There are some other features in there, but I haven't dived into them too deeply yet. So just going to touch on the key one that people might want to make use of. So we're going to start with this code for the rest of the session. Now, the important thing about this code is you shouldn't copy this and put it into your code bases. There are some obvious mistakes in this code, perhaps not so obvious mistakes actually, but there's some things that we're going to improve as we go through the session. So consider this our starting point. And as we go through, what we're going to do is refactor this code, incrementally improving it, making use of some of the features as we go. Now, this is a controller. If you're using ASP.NET Core, you'll have come across controllers. So we're imagining that in our scenario here, we've got a controller on our web API that people can call into. And in order for that to fulfill our client's request, we're going to make an external call out to, in this case, GitHub, to just pull back a list of repositories. Now, this uses an old URL. The ASP.NET Core repositories have actually moved since I put these slides together, but it's basically the same idea wherever you're calling out to. So fundamentally, what we're doing is creating that HTTP request, sending it, getting back the response. In this case, we deserialize it into a little sort of type that represents our model and then just return it. It's not doing anything super exciting, but this will be quite common across certain applications, particularly if you're building microservices. Microservices tend to get, not necessarily always in the best form, get quite chatty. And you will find yourself making calls from service to service at time where you need to kind of fulfill a request response type situation. So the first thing I want to call out about this code that is a kind of warning flag, if you're aware of kind of some of the pitfalls of HTTP client is this using code here. So we're basically newing up a HTTP client instance, we're using it to make the request, and at the end we let it get disposed. Now this looks reasonable because HTTP client itself implements iDisposable. And so, you know, as developers, we've been taught really that if you see and you are consuming a type that is iDisposable, we should do the right thing and dispose of it when we're done. Unfortunately, the way HTTP client works and the effects that that actually has are not too obvious necessarily. So when we create a new HTTP client, we also underneath that end up creating a socket chain, really, a connection chain that actually makes the request out. So we have a series of delegating handlers or handlers that are responsible for sort of forming and shaping the HTTP request. They will then need a network connection. So a connection will be open from the connection pool and they'll be able to make the request. What happens when we dispose HTTP client is we also dispose of that handler chain and we dispose of the connection pool at the end of that handler chain as well. And so what this means is if we have code like this, particularly in something like a controller, which might be called very often, you know, this could be called in a heavy service many times a minute, many times a second even, we're going to create these HTTP clients. We're going to then quickly dispose of them. And this constant creation and disposal means that we are opening new sockets every time, and then we're closing them almost immediately. The problem this brings is in the way that sort of TCP works in principle. So when we close the socket on our end, it doesn't immediately free up the port that we were using for reuse by the operating system. It goes into what's known as a time wait state. And this time wait state is a period of around 4 minutes on Windows, where that socket is essentially sort of reserved by the operating system. So it's not going to be allocated to any other processes because technically speaking, there could still be traffic coming to that socket that was destined for our process. And even if we've said we're not needing it anymore, we don't want the operating system to reallocate that socket to something else and it's suddenly to get some sort of latent packets coming through. So time wait is part of a mechanism that tries to prevent that kind of behavior. And there are a limited number of ports on a system. On Windows, it's just over 16,000 ephemeral ports that are available. And these are the ports that are available to processes like our application here to make outbound connections from. And so 16,000 sounds like a huge number, but you don't need many of these kind of action methods on a particularly heavy service to start seeing the effects of this constant creation and disposal of HTTP client, causing a situation where we might run out of available sockets. And this is a situation known as socket exhaustion. And you will get an exception if this happens, because the operating system will essentially be able to, we'll want to open a new connection to handle the next request that comes in. The OS will say, no, I can't give you one at the moment. I don't have any. And then we're kind of stuck. What does our application do? The other risk as well is that this could affect other applications on that server. If you're running more than one web server or website off of that server, that could potentially starve the pool of available sockets that affects all of those other sort of processes that are running on the same system. So this is a problem that we can run into. Now, this problem, as I will show you, has been sort of cleared up in a couple of ways, particularly since .NET Core 2.1. But you have to do certain things to make sure that you take advantage of it. Just to show you what that socket exhaustion might look like. So I basically took that code that we just had there. I ran it in a tight loop of 20 times. And you can see when I do a netstat on my machine, I can see that I have these 20 different ports that were used to create outbound connections to the same IP address. And they're all now sat in this time wait state. So as I say, these now are basically stuck for about 4 minutes before they will then get released back in. And this is, the situation that we want to try and avoid in our applications if they need regular outbound connections. So what's the solution to this problem? Well, I'm going to show you what you might have done around sort of .NET Core 1.0 and 2.0 before we start looking at the more sort of useful solutions that we could take advantage of. But just to know how to solve this in a really simple way, the main thing that we could look to do is to reuse the HTTP client instances. So one way you might have done this in the past is inside your configure services method, which is how you configure the services available in dependency injection. We could add a registration in here for HTTP client. We can make it a singleton registration, meaning that once an instance has been created, that will persist for the life of the application. And whenever we resolve it from DI, we'll get that same instance time and time again. So at this point, we have the registration, and we could update our controller code to make use of that. So what we would do here is we'd accept via the constructor a HTTP client instance. ASP.NET Core's dependency injection, when it activates this controller, will provide that singleton HTTP client instance to us, and then we'll hold on to it in a private field. We don't then need to create a new HTTP client in our action method anymore, so we can drop rid of that code. But one of the problems that you would run across if you were following this approach is that this previous code was configuring on the client default request headers. So on HTTP client, you can set these default headers, and those will apply to any requests that go out through that client. Now, the risk here is that while HTTP client is documented as being thread safe from the perspective of its methods, it does point out that its properties are not thread safe. And what this means is if we have more than one thread that's using this same singleton instance at the same time, and they're both setting different types of headers in here, there is a risk that those headers could conflict with one another. So, we could have a race where two requests come into two different action methods in our system. Perhaps they're talking to different downstream services, so they'd set a different accept header. And suddenly then we could find that actually we're not sending the correct accept header through to GitHub by the time we actually make the call. So we can't actually set those default request headers to apply to every request as we did in the previous code. But there's quite a quick fix that we can do for now, which is just to set them on the HTTP request message itself. So now this means that we're only affecting that one request that we're actually making at the moment. So that's all very well and good. We've now corrected that problem. And then the final change that we'll make then is to use our injected HTTP client instance. And this code now is updated. And because we're reusing the same HTTP client instance across our application, wherever we're getting it from DI, then it means that we only have one delegating handler chain, and we only have one connection pool at the end of that. And that means that once the connection's opened, it can sit in that connection pool when it's finished making a request, and the next request that needs to be sent can go over that same connection if it's to the same endpoint. And so in this scenario, if we've got lots of requests coming into us and they're all constantly calling out to the GitHub API, we can just keep reusing the same few requests probably in our system without running the risk of socket exhaustion. Unfortunately, in software development, there's always a but to these things. And the but in this case is the side effect of doing this is that we might run into issues with DNS. So now what we're doing is we're saying to basically reuse the connections for as long as that connection pool lives and as long as the handler chain lives, which is all controlled by that singleton HTTP client instance. And what this basically means is that once we open a connection to api.github.com, in principle, that connection might live for the lifetime of the application. But typically today, we're very reliant on DNS for updates to servers that we should be actually communicating with. Now, something like GitHub might not be too bad. It's usually going to be pretty steady. But if you're doing this internally, particularly in a microservices environment, perhaps you're running lots of containers, those things come up and down on different IP addresses all of the time. And that's kind of part of the sort of pros of building in that way, is that we can sort of spin up new instances of these things very quickly. But it doesn't necessarily guarantee that the IP address that we've been handed as a client is going to remain constant for the life of our application. And so what this means is that at some point in time, that DNS may no longer point to a valid server, and we might get a failure, which will then cause the connection to drop. But it does mean that our client request is likely going to have to handle that failure. And that may add delays into the calls that we're making. The other risk here as well is around situations where perhaps you're talking to services that are kind of behind a blue-green deployment. And typically what happens there is you'll have your sort of two systems running side by side, possibly both publicly available at the same time. You'll have production and maybe staging. And as part of the switchover, when someone deploys a new instance, they will deploy into staging the new version, test it, and when they're happy, flip the IP that represents what the live production version is using DNS. And now if we're not refreshing our DNS from time to time, then we're never going to pick that change up. So we might end up talking to an outdated instance of the server for a period of time without really realizing it. And that may or may not be a problem in your environment. So that means we've kind of solved one problem and created another. And this was a big issue for people in .NET Core 1.0. Leading up to around 2.0, there was a long-running GitHub issue that discussed the problems of this approach, the pros and cons of, avoiding socket exhaustion, but at the risk of potentially running into stale DNS. And so around the 2.1 timeframe, the ASP.NET team were working on a potential solution for this called HttP Client Factory. Now, in fact, as we'll talk about a little bit later, the .NET team itself were also working on a solution that worked at the kind of HTTP client level as well. And both teams were working on a solution because I think at the time, fundamentally, neither knew which was going to be able to land first, and they wanted to solve this problem. So the ASP.NET Core solution, which was this HttP Client Factory feature, was designed to handle a few things. So one of the things it was going to look at is managing the lifetime of the HTTP message handler chain. So those are the things that ultimately own those connection pools, which own the connections. And so by managing the lifetime of those, we can manage how long connections are going to be used for. But it does other things. It also provides a central configuration for providing sort of logical configuration of named instances of HTTP client. So if you're talking to more than one downstream system to different endpoints, you can provide configuration that relates to each of those systems in a kind of centralized place and get that reuse across your code base. It also codifies the concept of outgoing middleware using delegating handlers. You could always use delegating handlers with HTTP client manually, but it was just a little bit of a pain to build the handler chain that you needed to manually and then sort of attach it to your HTTP client. So with HTTP Client Factory, they've tried to make that a little bit easier with kind of fluent configuration. It integrates with Poly, which we'll talk about more later as well. But fundamentally, this is about handling transient faults. And it also provided some improved diagnostics and logging scenarios as well. So with that in mind, let's look at how we can convert our code to start using this new feature. So let's go back to our startup class here. And what we're going to do is we're going to adjust our registration here. And we're going to get rid of our singleton HTTP client registration. And we're going to swap that for a call to add HTTP client. So this will be available to you if you're using ASP.NET Core 2.1 or greater. Or if you're using an environment where you don't have ASP.NET Core, maybe you're using a worker service, for example, then you could actually bring this in manually using the Microsoft.extensions.http package. And that will also give you this extension method. And this extension method registers the HttP Client Factory feature into DI along with a bunch of additional related services. Now we can go back to our controller, and rather than injecting the HTTP client into our controller, what we're going to inject instead is HttP Client Factory. So this is a factory that can give us HTTP client instances when we need them. And now we can update our actual action method. So of course, we don't have a HTTP client instance here that we'll use. So we have to first create one. And so on the factory, we can call create client. That gives us a HTTP client that we basically should treat as a kind of transient instance. Although we're going to get new HTTP client instances every time we call this method, internally, it will manage the delegating handler chain, which, as I say, holds onto the connections at the end of it, and it will manage the lifetime of that, reattaching it to the clients it's giving you for a period of 2 minutes by default. And that is configurable, of course. So this means that what we're going to do is basically say that we want connections to live for a maximum of 2 minutes, after which time, once no one's using them anymore, we want them to be freed up, returned to the operating system, and then a new connection established for the next request. And this is what's happening internally for you by the factory. And you don't have to worry about that. You just call create client. It gives you an instance, and then you can use it. And that's what we're doing here. The next way that we can use this is to kind of take it a step further and start using one of two ways that we can configure these logical kind of client definitions that we have for different services that we're talking to. And the first is named clients. So what we do when we do a named client is we're going to provide some configuration associated with a particular name that we want to use whenever we're calling a particular service. So instead of using just the raw add HTTP client method here, I'm going to use an overload that takes in a name. In this case, we'll call this GitHub. It's just a string. And then optionally, we can provide it this delegate, which can configure the HTTP client. And the way this works is every time the factory is asked for a new client through that create client method, it will create a new instance, attach maybe an existing handler chain or a new one. And then before it hands it to us, it will run this configuration delegate here to set the client instance up. And you remember earlier we had those issues with being sort of thread safe with the HTTP client. We're now, because we're using them from the factory and we're anticipating that those are going to be short-lived HTTP client instances. And once we're creating one for a particular endpoint, we're only ever going to use it to call that particular endpoint. What we can do here is we can configure those things like the base address, like the default request headers that we're going to need whenever we communicate with GitHub. And so now we have this central configuration that we don't have to update in multiple places across our code base if we are making requests from lots of different action methods, for example. So now we can update our action method. So our URL that we're going to actually call here can change. We don't need the host because we are actually setting that up on the actual HTTP client instance itself. So we just need the path that we're going to call. We don't need to set these per request headers anymore because we're expecting those to be coming from our configured named HTTP client instance from the factory. And then finally, when we ask the factory to create a client, we can give it the name of the client that we want, in this case, the GitHub named client. And now we'll get back an instance of that. And as I say, this is going to be totally thread safe. We should only be using it from this single thread. It's transient. It will be disposed of, or in this case, it will just be discarded at the end of this method. We don't need to dispose here. And we'll talk more about the reasons why later. And now we're actually using that configured named client. And that's kind of cool. It's kind of useful. There's a little bit of stuff I don't like about named clients. You've got magic strings kicking around. You could solve that with constant strings in your application. But where the real power, I think, comes from is using typed clients, which is taking this concept to the next step. So a typed client is simply a class. So here I've got a class called GitHub client. I've decided to create an interface that represents the methods on this class, but you don't have to have an interface. That's optional and a preference for your application. But the one requirement of this class is that it must, in its constructor, at least accept HTTP client. Now, it's going to get this through the client factory. When the client factory is creating this typed client, it's going to manage giving us a unique HTTP client instance, again, potentially with the same handler chain, with the same connections on the end of it, but it's going to inject that for us. Now, because we're configuring or we're creating a client here that represents communicating with GitHub, and it's basically our abstraction over the GitHub API for the bits that we care about, we can do our configuration if we want to in the constructor of this type. You can still use typed clients with the configuration with the delegate, as we just saw with the named client in the startup class. But I much prefer to put this code where it kind of lives. It feels much more sort of the right responsibility that this kind of configuration lives. So we've got the constructor to set this thing up, and now we can create methods on here. So what I've done here is I've created a method that is basically a copy of what we were doing in the controller directly. But now we've kind of given it a proper name. We could, we can put tests around this. This is our single responsibility class that represents talking to the GitHub API. In this case, we only have one requirement, but there could be many methods here that we implement. And internally, we then deal with all of the logistics of, forming the request, sending it, and dealing with the response. So now, if we go back to the configure services method, I'm going to get rid of the named client, but you can have more than one named client. You can have some named clients, some typed clients in this same configuration. You just keep listing services.add HTTP client and then set up the next one. But for the sort of purposes of fitting this onto one screen, I'll get rid of the named one for now. So here I'm registering my typed client now, which can be done in one of two ways. Basically, we can provide it just the GitHub client implementation if we don't have an interface, or if we want to put it behind an interface, as we've chosen to do here, then we register that first. And that gives us a service type and then the actual implementation type. The reason this is nice is, as you'll see later, is when we start using this typed client in places, we can inject the interface. And if we've got classes then that we want to test, we can test with different responses if we give different results from our methods there. So we've registered the typed client. In the controller now, what I'm going to do is inject the typed client directly rather than the HTTP client factory. So now this is already a little bit clearer in my opinion. The controller, if we take a look at its dependencies, we can reason quite easily that we're going to be communicating with GitHub from here because we have a GitHub client. Before, we just could tell that we were going to make a HTTP request somewhere. Now in our action method, we have all this code that we had previously to create the message and send it. In my opinion, again, this doesn't really live inside the controller. This is not really the responsibility of an ASP.NET Core controller to do, create a message, send it, deserialize it. That's kind of additional domain stuff that shouldn't really be the purpose of a controller, in my opinion. So for sort of a clean code, we've now abstracted all of that logic over to our typed client. So our controller code gets a lot simpler and is much more about, taking a request from the user, calling some service that can fulfill it with the data it needs, and then returning a model back. So in this case, we call the GitHub client, we call our get ASP.NET repos async method, and now we have the data that we need. So let's sort of switch gears slightly and start talking about this idea of outgoing middleware, which I hinted at earlier. So from a sort of high level abstraction point of view, the way it looks to us at the moment is our application code calls HTTP client. HTTP client sends the HTTP request message that we pass to it to whatever endpoint it's configured to send it to. The endpoint returns a response that gets converted back to a HTTP response message and then gets handed back to our application code. What's actually happening under the covers is that underneath HTTP client is that handler chain that I mentioned earlier. And much of this is the system level stuff that's part of the .NET framework that's responsible for, establishing connections, establishing, converting the HTTP request message into an actual request and kind of forming it and to send it over the wire. So below us, we have at least these two handlers are generally involved, but actually there's usually a lot more that stack up as part of this handler chain. And it's not really too important to understand what that chain is. I have got a blog post that kind of covers it if you're interested, but it's important just to know that that handler chain exists. More importantly, it's important to know that you can actually add your own handlers into this chain. And so these have the opportunity, as a request message flows through and out, they have the opportunity to inspect that message and potentially adjust it, change it, add stuff to it. Similarly, when the response comes back through, those handlers have the opportunity to see the response coming through and maybe read some data off early for their own purposes. So scenarios where you might use this are potentially any kind of sort of diagnostics or logging that you might want to be doing in your applications. So if you want to know, what's the success rate of all the requests going out of your application, one way you might achieve getting that data, particularly before we had such good diagnostics in the framework, is to actually just put a handler in to handle that. Other scenarios you might have is if you're talking to downstream systems where you need to authenticate, and so you maybe need to go off to an identity server to get a bearer token and attach it. That's kind of logic that you could also implement inside one of these handlers. So as the request flows through, you can call out to the identity server, get your temporary bearer token, apply it to the headers before you pass it on to the rest of the system, that kind of thing. So let's look at how we create one. So again, it's a pretty simple class, and it derives from the abstract-based delegating handler class. So we can then implement on top of that. So in this particular scenario, because we're going to be using these with the client factory feature, we can accept services via DI. So in this case, I'm injecting an I monitoring service. This is just some sort of fake service in my system that will allow us to do monitoring. And then we override the send async method off of the base class. That takes a request message and a cancellation token and returns a HTTP response message or a task of HTTP response message. So what this means is that we can potentially do stuff with that request before we pass it along, which we're not doing here, but we could do before we call this base.sendAsync. And what base.sendAsync does is call the next handler in the chain. So however these have been registered in whatever order, it will just call the next one, passing on the request. Once the response has been returned to the system and it's flown back through some of the other delegating handlers further down the chain, it'll eventually come back to us in this response here. And so what we can do is we can access that response, and in this scenario, perhaps record just a simple metric that says what the status code numbers are that we're receiving back. And you can imagine scenarios where this would be useful if you have got monitoring, if you want to alert when your failure rate starts to increase, you could then proactively go and investigate that. So this is a really simple example, but it's the kind of thing that you might want to do with these delegating handlers. So how do we register these? Well, fortunately, because we're using this HTTP client factory, it supports a kind of fluent configuration of either named or typed clients, because it's basically a builder. So it's an HTTP client factory builder at this stage that lets us flow calls to all of the configuration we want to apply. So in this particular example, what we'll do is we'll call add HTTP message handler, and we'll provide it the type that represents our handler. And now this will get registered into the pipeline running prior to the system sort of handlers that do the final sending of the message. And we can register one of these. We can register multiple handlers if we want to. The ones at the top will run first, and then you can order them as necessary. The other important point that you must do here is you must also make sure that you've manually registered your handler as a transit type into DI. For some reason, that wasn't done automatically by the team. I think they didn't want it to be a bit too magic. And so you're responsible for registering that yourself. And that's all we need to do to add that metrics handler with our kind of cross-cutting concerns that will apply whenever we call out through our tight GitHub client there. So we're going to get metrics across all requests to all endpoints of that service. Let's switch again and start thinking about other kinds of problems with HTTP. So one of the big problems with HTTP is there's no real guarantees. Unfortunately, all sorts of things can affect a request and a response actually completing. Networks can fall over, servers at the other end of the connection might temporarily not be available. And so we do have to think about how our applications are resilient to those kind of transient faults in the system. And this becomes more and more important if you're building sort of microservices in particular, where, if you've got lots of interconnected chains, what you don't want is failures in one system to bring down, the whole of your application. You'll be familiar with this concept perhaps from people like Netflix and their chaos monkey concept, where they basically kill off random services to make sure that it doesn't, bring the whole system down. And that's what we're really talking about when we talk about sort of being resilient to these kinds of failures. So Poly is a third-party open source library. It's up on GitHub that you can pull down, and it's responsible for providing mechanisms to handle common kinds of transient issues in a quite nice way. So basically what it gives you back is it gives you back a configured policy that defines under certain circumstances what it will do. And then you execute your code within that policy, and then it's responsible for doing things. So in this case, for example, it might be a retry policy that retries the request if it fails for a certain number of times. Or it can end up being more complex policies. So things like circuit breakers. So if the downstream system is constantly failing across lots of different calls, across maybe our wider application, not just one place that's making these calls, but across all of our app, what do we do if it's constantly failing? Well, perhaps we apply a circuit breaker, which basically means we stop trying to call the service. This might give it enough time to recover. If we're constantly hitting a service as it's trying to recover, that can just kind of prolong the issue. So a circuit breaker means that we stop trying to call it, give it a break, and also it means our code can kind of short circuit and fail fast. And of course, you need to think about what you do in that scenario, which is why there's things like fallback policies. There's another policy that you might apply. So if after retrying or the circuit's broken, I can't get a response, what can I do instead? And maybe that's I go to the cache policy and I use a cached version of the value, or maybe I give back some meaningful default. Timeouts are also quite useful. So, how long do you want to try a thing before you give up? Things like bulkhead isolation are a little bit more about that sort of wider avoiding of cascading failures. So, if a downstream system's struggling and then we're calling it more often to try and, get requests because we're retrying all the time, that can actually add load to our service. And perhaps we can start to, run into issues with socket exhaustion, or we're spending too much CPU time constantly trying to make these calls. And so what we can do is put requests through this bulkhead, which essentially limits the impact of such things. It's kind of named after bulkheads on a ship, where the idea is that the bulkheads prevent a damaged hull from flooding the entire ship. And it's the same concept here. If there's one thing that's not working quite right, we don't want it to bring the whole system down. And all of these can be combined together into what's known as a policy wrap as well. And that's very common, that you'll probably combine at least 2 or 3 of these. You might retry for a certain amount of time within a timeout. You might then fall back to a plan B, or you might fall back to a cache. So you'd wrap those policies up into a chain, and Poly will execute them for you. So just to kind of make sure that the point's really clear on the retry one, because this is the most useful, I think, for HTTP requests. Imagine that we try and send a request to a server, and that server is currently unavailable. It's on fire in this scenario. So the fact that we get a 503 is probably pretty good. But we get back a 503 because the server can't give us an answer right now. Now, in a normal situation, then we'd just fail at that point, and whoever called us, we'd have to fail to them as well. But if we implement poly and retries, what we do is we'll make that same request and we'll get back a 503. And then instead of just giving up, our poly retry policy can kick in and it can say we'll automatically re-execute that request for us. And maybe we set that policy up to try a couple of times. So after this second attempt, we still failed, but maybe after that point, someone recovers the fault at the downstream service that we're talking to. And so when poly does to another retry for us, this time perhaps we get a 200 OK. So there is a downside that we might have made a slight delay in how quickly we've been able to respond to this request from our client, but at least we have given them an answer. And that's often better than failing fast and not being able to provide anything. So how do we use poly with HTTP Client Factory? Well, again, unfortunately, this has been made pretty simple because the Microsoft team and the poly team actually work together to basically provide an integration for these two products, which was really good. And I had the opportunity to work with them on this as well, giving a bit of feedback at the time they were designing this as to kind of how, as a consumer, I would use it. And they've ended up on what I think is quite a nice approach. So what we can do is we can call another Fluent configuration method on the Client Factory builder here, which is called add transient HTTP error policy. And what this does is say, okay, I want to add in a pre-configured policy that's going to wrap my HTTP calls. And that pre-configured policy is going to be set up for us on our behalf to handle things like, temporary unavailable responses from the server. So maybe any kind of 500 error, any kind of timeout errors, or perhaps just a request failure because it timed out on the client side as well. Once we're setting this up, what we get given is a policy builder, and that policy builder is how we actually define what to do when any of those failure situations occurs. So in this case, what we're saying is register a wait and retry policy, and on that policy, configure it to wait and retry up to 3 times. So it gives us a few bites at the apple before we give up entirely. And then inside this call here, we define the retry time. And this could be a fixed value. So every request, we wait the same amount of time. But what's more common is what we're doing here, which is to calculate an exponential backoff, which basically says, progressively delay longer and longer in your retries before trying again. And the reason you probably want to do this is if you retry after maybe a few hundred milliseconds and it's still down, then it's probably not just a transient one-off issue. Maybe there's a bigger server issue. So maybe we want to wait near a second or 2 seconds or 4 seconds, progressively back off and give it more time to complete. So with this registered, now whenever we make calls through our typed client, they're always going to go through that policy and we get retry logic added in. We don't have to code it in our own code manually. And we can dynamically apply policies as well. And this is quite important with HTTP because you need to think about idempotency. So GET requests should be safe and idempotent. They shouldn't be affecting the downstream system if you want to repeat a GET request. But you can't make the same guarantees, for example, about POST requests, which might be creating an object. So imagine the scenario where you've tried to send a POST request, it fails, and so you allow poly to retry that. The problem is you don't know where the failure occurred, and possibly your POST request was received by the server, processed, but it was their response that never reached you. And so in that scenario, the object that you've tried to create has already been created. And if you're not careful in systems that don't sort of deduplicate or don't have some way of dealing with that kind of situation, then those might end up reapplying or creating new duplicate instances of objects, for example. I'll just see a question come into the chat, which probably just jump onto since we're talking about poly. So this came from, have you found any difference between the Microsoft extensions.http poly package and the poly package? Not really. The poly package allows you, as we're about to see actually, to create policies more specifically. The Microsoft extension one is just really a linker between them. So it gives you those extension methods on the client builder so that you can register the policies into the chain, and it pre-configures that kind of sort of HTTP policy that knows how to deal with the common error codes. But otherwise, it's leaning on poly under the hood to do things for you. So it's kind of just really a linker library, if you will, between the two. The reason it wasn't shipped in the box with ASP.NET Core, so you actually do have to reference that library manually, is that Microsoft kind of have a contract with users that they're not going to depend on any third parties automatically on your behalf. You need to opt into those for the most part. And so other than things like probably Newtonsoft.Json, I think everything else you kind of opt into these days. It's the same with Poly. You have to choose you want to have that library in your system with the fact that you're taking a dependency on Poly itself, and then you can continue to use it. So let's go back to this concept of dynamic policies. So how do we do that? Well, this is where we use Poly's library directly in our code. So here, for example, we're going to set up two policies that have the same essential policy signature, but that will do different things. So the first one we use is we're going to use the policy sort of static type here to allow us to create a no-op policy. And what a no-op policy means is it's just going to run our code once, and if something fails, it's not going to do anything. So that might seem useless on the outside, but when you combine it in a minute, you'll see why that's handy. So the next thing we'll do is create a retry policy, and this is the manual way of doing it with Poly. So Poly includes some extensions as well, so that we can pre-configure this policy that handles things like 500 errors, 408 timeouts, exceptions, those kind of things. And then we set up our wait and retry as we did before. So now we've got two different policies, and because they kind of derive from the same base type, we can now actually, when we call add policy handler on the HTTP client factory builder thing here, we can actually say, well, we'll apply a policy conditionally actually. So if we're doing a get, then attach the retry policy as the request is being sent, but otherwise attach no ops. So now what we're saying is, well, we're happy to retry up to 3 times on gets, but for any other HTTP method, actually, we just want to try once, and if we fail, we fail. And this will need to be customized to your circumstances. If you own the downstream services, you might be able to make guarantees about the safety of repeating a same post request, but you do need to consider that in your code. Another quick thing I want to point out, because a few people that use Poly might have come across this idea of the policy registry. So Poly adds this idea of a registry for policies so that you can reuse them across your code base. So here what we're going to do is we're going to set the, we're going to create 2 different timeouts that we might want to use in our application. And we're going to set up a policy registry and add it into dependency injection. So this would be in your configure services method. We then can, on that policy, add the policies in and give them a name. And so this means that wherever we need those in our application, we can just extract them by injecting the policy registry and then retrieving the policy. But it also means that when we set up the client, as we're doing here, we can actually say we want to add a policy from the registry. In this case, we can define that we're using the regular timeout on this particular typed client. So this gives us that kind of flexibility to kind of couple these things together for our needs. One last kind of tip, I think, around HTTP Client Factory in particular, a few people asked this question when it first came out, was, well, this is all great, but what about situations where I needed to configure things like using certificates with the downstream service? And the way you configure certificates in sort of .NET is that you have to actually define and create your HTTP client handler directly, and then set properties on it. So here we're setting properties to add certificate authentication, for example. The way we do this with HTTP Client Factory, if you're using that, is you can actually call its configure primary HTTP message handler method on the builder. And this says that whenever this typed client is being created and there isn't an existing handler chain with connections that you're going to reuse, then when you're creating the handler chain, call this factory to actually create the handler chain before you attach it. So we can have complete control if we need it for those less common scenarios. So that's the main stuff I wanted to talk around about HTTP Client Factory, how it's useful. I want to go on to other HTTP tips now quickly, because there are some other issues with our code that we can improve on. And we'll do that, and then we'll start just talking a little bit at the end around some of the other ways that HTTP clients change through .NET Core. So the first important point I want to draw out is in applications where you are a little bit concerned, or even slightly concerned with performance and avoiding allocations, which is very common in microservices where you're trying to run on a small footprint. One of the common mistakes with the use of HTTP client is people will allocate for the responses more than they need to. So let me show you what's happening here. So in our code at the moment, when we've got our response back, we are accessing the content and we're calling reader string async to get a string. and then we're using that string so that we can pass it into, in this case, Newtonsoft.Json to deserialize for us. And that seems reasonable because we want a typed representation of the JSON data. We know we're getting back an array of repositories and we want to convert them to our GitHub repo type. So on the face of it, this code might not sort of sing out as problematic, but you have to consider the fact that that string that we're creating here is really just a transfer object to get into Newtonsoft.Json. The thing that we actually want is the IEnumerable of GitHub repo, and we're using a string as a kind of intermediary type. The risks that this introduces is if the response body is large, then not only have we got a large stream of bytes coming back to us, but then we have a large string that we're creating on the heap, and then we're creating our actual final object that we're actually going to use. And essentially that string then is no longer needed, so it will end up getting garbage collected. But if the response is really big, then maybe that string ends up on the large object heap, and that requires larger, more complex garbage collection processes to recover. And so that could have sort of bigger impacts. The other risk here is as well, depending on who you're calling, if you don't necessarily trust the downstream service, i.e. it's outside of your network, then someone could potentially get in the middle of your request or compromise the downstream system and return a maliciously large payload. And if obviously we're still going to get the bytes of that regardless, but then not only are we getting a large, malicious, maybe 1 GB payload of bytes, but then we try and turn that into a 1 GB plus string to then try and pass it into the deserializer. So we can avoid this entirely because Newtonsoft.Json supports working with streams, and we can get a stream directly off of the response content. And you could do this manually. It just takes a little bit of configuration. It's a few lines of code. It's not too bad, but actually what was quite common and quite popular was to use an extension method that was available in Microsoft.ASP.NET.WebAPI.Client, which is a NuGet package you could bring into your application. I think it was added by default in ASP.NET Core 2.1 sort of time frame. So what that package allows us to do is call this kind of handy extension method, which is read as async, and then we just pass the type. So it handles taking the response content stream and using the streaming APIs of Newtonsoft.Json to turn that into the raw bytes. Now, unfortunately, it wasn't fully asynchronous because Newtonsoft.Json wasn't supporting async all the way through the chain, but it was still much more efficient than having that intermediary string. A little bonus tip that I've added in this morning is .NET 5 actually includes a slightly different way of approaching this. So in .NET Core 3.1, they introduced a new sort of JSON serializer called System.Text.Json, which is in the box. In .NET 5, they've introduced some additional extension methods to make using this JSON library for serialization and deserialization easier in .NET situations with HTTP client. So here I've updated to use that library, which ships in the box, but you just need a using statement for system.net.http.json. And that gives us access to this read from JSON async. So this looks very similar to the one from the Web API client library that we just saw. But now we're using the System.Text.Json high performance serializer to handle that deserialization for us. But functionally, it's still a one-liner piece of code. And so in this scenario, we just avoided that string. The main reason I see people wanting to continue to use like a read a string async and then deserialize is for debugging. Quite a lot of people want to put a breakpoint after that string has been created so that they can see what the raw JSON string looks like and understand what's gone wrong before they see serialization errors. But you can do that, but just remember to take it back out before you go to prod. And it's much better to not have that in your production code if you can avoid it. The next thing I want to talk about is handling errors. So we've already talked about transient errors. These are the errors that occur, because of network issues or downstream servers being temporarily unavailable. But sometimes we might get a legitimate error back from the server. And if you look at this code that we've got currently, we're not dealing with that. So we're getting a response, and we're just going to read its content into this type of ours, which is fine if we've actually got response content, but we don't know. Maybe we got back a 404, maybe we got back some other, bad request type status code that means we don't have content because we didn't get a successful response. So it's always worth making sure that we check for that. A couple of ways you can do this. We can first call, ensure success status code on the response. And what this does is if it's a 200 state range status code, so 200 to 299, it just passes through this method. But if it's any other sort of status code, then it's actually going to throw an exception at this point. And then we can, in our sort of code further downstream, we'd have to obviously catch that and deal with it. But at least it means we're not going to try and deserialize and throw a deserialization exception. A slightly nicer option here might be to do this, which is where we conditionally deserialize or return a fallback value. So we're just going to say if this is a success status code, then do the deserialization. Otherwise, return just an empty array. I've left out for brevity here. It's still possible you've got a success status code, but the content's empty. So you might do other checks as well before you deserialize to make sure that the content length is greater than 0, for example. You know, there's other stuff to do here. And it's this kind of logic that fortunately is dealt with by the extension library that I showed you before as well. So they won't try and deserialize a 0 content length stream, for example. The next thing is cancellation. So another way of being efficient in our applications is to avoid doing work that we don't need to. So let's look at this scenario. So we've got this typed client. It's going to make a HTTP call. But what if the caller of our application goes away? So they make a request to our endpoint then calls into this typed client, starts making a HTTP request, but our consumer has gone away, they've dropped their connection, or they've cancelled. Is it worth still sending the request message? Is it worth still deserializing it into an object when we know that no one needs it anymore? Probably not. So we can avoid that by using the common sort of cooperative cancellation of the sort of async await library. So we'll add the support for a cancellation token, an optional cancellation token on our method here. And then what we can do is before we send the request, we'll do a check to make sure, see if we're cancelled already. It's unlikely that we'd be cancelled that quickly, but it's possible. And in this case, if we exit early, we'll have an exception thrown here, but it means we won't even try and send the request, which means we might not even create a network connection if one needed to be. So this is resources that we're avoiding using here. We can also pass along the cancellation token in our send async and as our read as async methods here. So we can just pass it on to those which support cancellation tokens natively. Now, the only challenge here is we're calling this from an action method. So how do we get a cancellation token to pass into the type client? A little known fact is that ASP.NET Core supports injecting a cancellation token for you into the action method when it invokes it. And as long as we just accept one here, we will get a cancellation token that's tied to the ongoing request that we're handling. So if our consumer cancels or drops the connection, then we should see that cancellation token be signaled. And then we can then pass that into our code as we're doing here. So these little tips and tricks are just niceties that you can build on top of what you're probably already doing just to make things a little bit more performant and take advantages of the features that are there. The final one that's also quite interesting for, again, quite niche high performance scenarios where you might want this is to make use of this HTTP completion option. So what this does is by default, when we send async here with HTTP client, by default, what happens is when the response comes in, it gets streamed into a temporary internal buffer. And once it's in that internal buffer, what it means is HTTP client can end its request with the server, freeing up that connection for someone else to reuse. So it basically ensures that that connection is kind of rapidly released. The downside of this is obviously we're buffering everything into this internal buffer, so there are allocations involved there, but it's also going to get sort of tied up potentially, waiting for all of that data to come in before this can return. So send async here is only going to return once it's streamed that stuff into the buffer. So what we can do is, if we want control of that, we can actually pass in one of the HTTP completion options, which is the not the default one, basically, which says response headers read. So what this means is now send async will complete as soon as the response headers have been parsed off of the responses coming in. Then we get the response returned to us. Meanwhile, that connection is still established with the server and data might still be streaming in, but it just means that we don't have to necessarily start consuming it immediately. And where you might use this is if you've got key headers coming back to you that signal whether or not you actually want to even read the content, this might be a more efficient way of doing it, because you can very quickly check those headers, and in situations where they determine you don't need the content, you can fail exit quickly. There is a risk here in that we must make sure that we now dispose of the response message. And the reason we do this is the default behavior automatically releases that connection back to the connection pool so that the next request can use it. But in this scenario, because we're only saying, give us the headers back, we have to signal to it when we're done with the content. And so in this scenario, if there's any exceptions inside our deserialization, for example, that might mean that the response is never actually sort of properly disposed of unless we put it into this try finally block here. And this basically just means that we guarantee that we have the data that we need. I'm just going to have a quick look at some questions that have come in. Regarding read async, read as JSON async, isn't it the same or similar to as read as stream async? They're all similar. It depends what you need. So if you want the stream so that you can do something with a stream, you read as stream async and you get back that stream. But if you're going to then deserialize it into an object, then those convenience methods just mean that you don't have to do the handling of a stream and disposing of the stream manually. It's kind of wrapped up for you in a convenience method. Would you use read as stream async over read as JSON async? Personally, not very often. More often than not, I do want a deserialized object. So I'd say probably 95% of my code, 99% of my code, I'm using the convenience methods to convert JSON into an object. One from Lukash here. I wouldn't throw exception when cancellation occurred. I would just return an empty result. Yeah, so that's a decision that you need to make. You know, cooperative cancellation there's a few opinions on it, but the correct documentation recommends throwing if you're not going to deal with that cancellation in some appropriate way. So if you just want the caller of your method to be signaled via an operation cancelled exception that, you know, cancellation that they requested probably has actually completed, then that might be useful that they get that exception and confirm it. But in scenarios where you do want to return a default empty result, you know, you don't have to throw that cancellation exception if you don't need to. Another question, does HTTP client not dispose the response? Should we use configure await when using await? So two questions there. So disposal, I'm going to defer you to, because I have a few slides on disposal at the end, which hopefully demystify the rules a little bit around that, because it's not simple. And then the second part of that, should we use configure await when using await? It depends. If you're building libraries, yes, you should. But this is more an async await sort of world of problems. So inside ASP.NET Core, there is no synchronization context anymore. And so using configure await purely inside ASP.NET Core itself has no real effect, because it's not going to be trying to connect to a synchronization context on completion anyway. So you don't need to worry about it there. But if you're building a library and you don't know, you know, what platform that's going to be running on, it might not be ASP.NET Core, it might, you know, it might be a WinForms application, or, you know, something that does have a synchronization context, then typically, yes, you want to use configure await false there. So you signal that your code doesn't need to do that synchronization context handling. Yeah, there's a lot of stuff written about that. If you're really interested in that kind of stuff, then if you have a look out for .NETOS on YouTube, a few sort of friends of mine, one of them being Konrad Kokoska, they have a sort of series of videos on their YouTube channel, and they also have an async expert course that goes into a lot of that stuff. I haven't taken the course personally, but I've heard really good things, and that goes into all of the internals of like the async await mechanisms and how to use them correctly. That's worth checking out if you really want to dive into that. Cool, I think we're caught up on questions. So to answer the next question, it's almost like I knew this question was coming. When should I dispose? So the answer in sort of consultant type terms is it depends, unfortunately. And the reason it depends is, unfortunately, the disposal or the typical iDisposal rules don't necessarily apply to HTTP client and its types without knowing the internals of them. Unfortunately, I spent a lot of time digging through the code for HTTP client, trying to understand the rules and the internal implementation, and therefore when should you dispose. So the way I've narrowed it down is as follows. If you're using HTTP Client Factory, so that HTTP Client Factory feature, then the HTTP client instances you're getting should be considered transient already. And because you can dispose them, but it has no effect, basically, because the handler chain, the thing that really is disposable in the whole system, is being managed by the client factory itself. So even if you dispose of the HTTP client, it doesn't mean the handler chain is going to be disposed, because the client factory is managing it for you and its lifetime is internal, and it will dispose of it once it expires, which by default is after 2 minutes. It basically lets that expire and then it releases the connections. So HTTP client, when you're using HTTP client factory, I would just use it without any kind of disposal patterns. HTTP client without the factory, then the general rule is you never really want to dispose of it, because as we talked about earlier, if you dispose of it regularly, then you dispose of the handler chains, you dispose of the connections essentially and close the connections. And so that's where you can run into socket exhaustion if you're constantly creating lots of HTTP client instances and then disposing of them quickly. Of course, if you know in your scenario that it's a one-off request, then you could dispose of it immediately and that releases those connections straight away. But you run into more problems with socket exhaustion than you're likely to with DNS, but you need to factor in the DNS issue. HTTP request messages also are disposable. The reason for that is it might have stream content. So it's actually only ever has an effect if the content that you're sending on the request is a stream. And in that scenario, what you signal by disposing of a HTTP request message is you signal that once the stream has been sent, dispose of the stream. And so if you want that behavior, then yes, dispose of it. If you don't need that behavior because you're manually controlling the stream and you're disposing it later, then you don't need to dispose of the request message, I should say. So again, that one's quite nuanced and you need to understand, what effect you want to have. But if you're sending strings, string content directly, that kind of stuff, then it would have no effect anyway. HTTP response message, similar rule in that you generally don't need to dispose of it yourself, because generally the only kind of resource that you're holding onto is the connection. And the way it works by default is that, as I say, it will pre-buffer all of the response as soon as it can and immediately release that connection for reuse anyway. So that's the thing that you would potentially free up by disposing. There's no harmful effects if you do dispose in that scenario. It just has no real effect. The only time you need it is when you're using that response headers read option yourself, and you're basically then taking ownership for saying, I will let you know when I'm done with this connection and I've streamed everything from it that I want to. So hopefully that helps a little. As I say, it is a rather nuanced story. I have a much longer form blog post that kind of covers each of these things. So HTTP client, HTTP request message and response message individually. And I think I've included that in the resource link, which I'll share with you again at the end. Just a couple of things before we kind of get to the end. So something else, and I hinted at this at the beginning, in ASP.NET Core, or in 2.1 timeframe, the ASP.NET team built the HTTP client factory. At the exact same time, the .NET team, so these are two teams that work under the same umbrella, but they sort of do work obviously on different parts of the framework. The .NET team were working on the sockets HTTP handler. So what is this? So before this was introduced, basically the way that .NET Core worked, because it was cross-platform, it called down to OS APIs for things, for sending the requests, for actually doing HTTP. So on Linux, it's using libcurl, or it was using libcurl, and for Windows, it would fall back down to WinHTTP. So these are OS libraries for making the requests. The sockets HTTP handler is basically a new handler that's built as fully managed code. So it no longer calls into those platform level dependencies on the operating system. It knows how to create the raw bytes of a HTTP request message and pipe them over a socket. So it's now talking directly at the native socket level rather than going through an OS abstraction over the top of HTTP. The main reason they did this is, well, firstly, consistent behavior across platforms. So Linux, in .NET Core 2 and prior, was significantly slower for HTTP than Windows. Those gaps have now much been reduced. It was, when I last checked, still slightly less performant than Windows, but by far less of a margin. And that was down to some underlying socket behavior on the two platforms. But Fundamentally, it means now they have managed code that's consistent regardless of whether you're running your applications as containers on Linux or perhaps you're running them natively on Windows. Because it's managed code, the .NET team will be able to reason about that and optimize it. And so this sockets handler that uses this approach was enabled by default from 2.1 of .NET Core onwards. Doesn't at that time support HTTP2 though, so you would have to at 2.1 timeframe, you'd have had to have disabled it if you needed to do HTTP2, although that's now been solved. So this sockets HTTP handler also introduced a really nice additional feature, which is connection pooling with settings controller. So it provides this concept of a pooled connection lifetime, which is similar. If you've used .NET Framework's features for HTTP, you'll have come across Service Point Manager probably. And that was how you controlled essentially the DNS lifetime of connections that you were making. Pooled connection lifetime is a very similar concept, but in the .NET Core land. And basically what you can do with this is now you can set a maximum lifetime for a connection in the connection pool. You can also set an idle timeout as well. So we'll have a look at the two scenarios in a moment. But what this means is with this feature enabled and configured, we don't actually need the iHTTP Client Factory feature to manage the socket exhaustion DNS issue. You could use raw HTTP client with a configured connection pool lifetime to achieve the same result, whereby it will keep connections in use for a singleton HTTP client for a period of time. And once that expires, it will refresh them, which is kind of a quite nice place to get to. And the way this is configured is if you're using the HTTP client directly, is you create an instance of the socket HTTP handler and configure its properties as you need. So here what we're doing, I'm setting them all. You don't have to set all of these. But I'm saying I only want to allow a maximum of 5 outbound connections to this endpoint. I want to have a pooled connection lifetime of 2 minutes. So reuse the connections for a maximum of 2 minutes, after which start creating new connections for the next requests. But I'm also setting an idle timeout. So if a connection's idle for a minute, maybe it means we're not going to reuse it. So maybe we can release it more quickly. So we can have that kind of flexibility. And that's quite useful if you've got connections to different endpoints, some that are used all the time and some that are very infrequent. You can use these two to get a good balance if you're using HTTP client directly. Other things that were introduced, so in .NET Core 3, we got HTTP2 support in HTTP client. That was primarily added for the gRPC client scenario. It's not fully featured, so it didn't completely operate on the full spec, but it required enough for gRPC. It wasn't switched on by default, so basically on HTTP client, there's a version property that was added, and you could set that if you want to use version 2 rather than 1.1, which is the default. Or you could set that version also on the request message as well. Also in the 3.0 timeframe, they did some sort of improvements so they could support TLS 1.3, OpenSSL 1.1.1. And so those were available on Linux situations that meant that you could take advantage of some of the connection advantages of those underlying parts of the sort of HTTP world. So I've covered a lot of stuff. I'll do my summary and then I'll go to any final questions that are on there. So my general rule is if you're on .NET Core 2.1 or above, and really you should be because it's the only supported version, anything prior to that is not supported anymore anyway. 2.1 will be out of support reasonably soon as well, so bear that in mind. But if you've got 2.1 and you're using something like sort of ASP.NET Core, I'd use the Client Factory feature. Firstly, it gives you that kind of connection lifetime management, so you get the kind of socket reuse without DNS issues. Even if you want to configure that on raw HTTP client, as you can now do with that socket HTTP handler, I think there's other things that you might want to use on the factory, such as those, poly integrations, such as named and typed clients, particularly typed clients, because you're a great way to kind of sort of abstract around dealing with an endpoint. Do look at using poly for those transient fault situations. It's, once you get used to it, it's pretty straightforward. Just understanding what those policies look like and when you might want to use them and how you can combine them is probably the hardest part. But once you understand that, you can apply them pretty readily. And particularly, as I say, if you're doing microservices, really start thinking about resiliency scenarios. What do you do if a service is not there for a short period of time? Try and not blow up, try and retry it or do something else. be aware of that read as string async or get string async methods. So that intermediary string, unless you really want a string for some reason, and it's an allocation you can avoid if all you're then doing is deserializing from that string. So manually use read as stream async and then put the stream through the deserializer, or as I showed, use those extension methods that mean that you don't need to write that code yourself. Do expect and handle errors, transient errors, but also, servers returning you 404s and things like that. Make sure your code is considering that possibility. Pass cancellation tokens, as I say, you all have your own opinions about, whether you throw in on cancellation or whether you just kind of, return some kind of default response. That's totally fine. Either way is reasonable. As long as it's consistent within your team and code base, I'm not going to argue with you, but just make sure you're using them and passing them through where you can to avoid doing work you don't need to. There's no point sending requests if someone's cancelled the call to your code. Do try and dispose of appropriately. And so generally, you don't need to worry about disposing these types unless you're in those specific scenarios. So, if you are using the HTTP completion options response headers read, then yes, you do need to be a bit more responsible for disposing of the response when you're done with it. But under normal circumstances, you don't need to worry about that. Hopefully, with all that, you can kind of go, you can go and take a look at your code bases tomorrow and, enjoy code reviewing your peers as you see this kind of things coming through. They are easy mistakes to make. It's not, there's no reason to feel bad if you have got this in your code base today, because, I think it's got a little bit better, but the documentation was quite poor in these aspects originally. And as I say, the fact that you have to understand the scenarios when and when not to dispose makes that whole abstraction a bit leaky anyway. We just need to do the best we can. I mean, there's no harm in disposing if you prefer to for security reasons, but just go and have a good time. Hopefully don't make any errors. And if you're seeing, socket exhaustion in particular, hopefully you know now how to correct it. Just before I go to the questions, I do want to plug my latest Pluralsight course. This came out a couple of weeks ago. And I think it ties quite nicely into this content because although it's about logging and cross-cutting concerns of microservices, if you're doing microservices, the stuff we talked about tonight will be particularly useful. So you can get to this at bit.ly/.net-microservices-course, and that will take you straight here if you've got a subscription. If you don't have a subscription, it's 40% off at the moment on Pluralsight until I think it's Sunday. It might be tomorrow. It's part of the Black Friday sale, so you can go and save 40% on a subscription there if you need to. And then I'll wrap up by reminding you again, the bit.ly link .net-http will also take you to all of the resources I've showed you today. Do reach out to me if you have any questions. Search my blog for HTTP or HTTP client on my blog, and you will find all of my articles there manually as well if you want to. So let's have a quick look because we've got a bit of time. So let's see where I got to in the questions. Okay, so kind of continuing on from configure await, as mentioned, that there's a style cop rule. Do not directly await a task. May be removed when using ASP.NET Core microservice. I'm trying to think where that applies specifically to the question, but I think basically just saying that if you're in ASP.NET Core, I think it's saying you don't need to configure await then, I presume, which is good. From Damien, is there any easy way of capturing and forwarding correlation IDs between different HTTP clients within the request? Different HTTP clients within the request. So I'm assuming, yeah, we're talking microservices, so a chain of, one service talking to another and then maybe another. Fortunately, I'll jump back on my slides and just make sure that slides up. So this course actually talks about this. So it's talking about how to do logging across the microservices. And one of the things I talk about there is the built-in ASP.NET Core and .NET Core behaviors of supporting the open tracing headers. So by default, if you're using ASP.NET Core, it will accept the trace header coming in with on a request, and it will pass it automatically on to any downstream calls through HTTP client for you, which means that you basically get the same sort of trace ID through those requests. which can be used for that kind of correlation. If you want to do it a little bit more manually, then I have a library. Let's see if I can bring up a link for you. Correlation ID. I have a library here, which you can go to get on NuGet, which is also supporting correlation ID. So you can manually choose what header you read the correlation ID off of. It will attach it to a context that's available through ASP.NET Core, and then you can easily add that onto a downstream request. I'm not sure how good my documentation is on the project site these days, but yeah, I don't show it here. But I think in the docs I do show, yeah, hopefully, yeah. So I've created a specific extension method that you can use on the client builder here to add correlation ID forwarding, and then it will take that off of the context you're currently in and pass it on for you. So you can use the Microsoft built-in kind of tracing stuff if that's good enough for what you need. If you've got more specific environments, or you're not worried about full open tracing, then perhaps look at using this library. I'm starting to not update it as often as I once did, because I'm going to start doing a series of blog posts on the tracing that's built into Microsoft stuff now, because I think it's probably easier to use the defaults rather than bring in a third party that can essentially repeat the same thing. Question also, does it use Serilog brackets plural site course? So yes, it does. So for the logging, I show using Serilog to write to Elasticsearch, unsurprisingly, now that I'm employed by Elastic. So using Elasticsearch is basically creating an index that represents all of the logs from multiple microservices, so that we can do querying in Kibana across across requests that go across multiple services. So if that's something that's interesting to you, and hopefully, yeah, that's covered for you in the course. Looks like nearly done. One from Sean. I've been recommended to use refit. Will these work along with refit? I believe there is some degree that it will work. I've not used refit personally, I'm afraid to comment, but I do remember conversations with the ASP.NET team, and these are about a year and a half ago, where there was discussions on trying to sort of allow it to use refit in some way. I can't remember if they created some extension methods or refit might have done, but I'm afraid that's all I can remember. So you'll need to double check that one. Cool.